I just want to say it's always an honor to come here. This is my third time doing a lecture in this audience, and I really enjoy it a lot. And so this is intended to be pedagogical, so please interrupt me, ask me whatever questions, whatever piques your interest. And also I'm going to just talk a little bit about the things that I love about the science that I get to do. So I'm going to tell you a little bit about our research program. And again, feel free to interrupt me. But I'm also going to talk to you in sort of big picture about one of the things we're really excited about, which is just thinking about color and what you can do by making materials that absorb and emit just beyond where the eyes can see. So just a reminder, this is probably something you teach in your classes. Certainly I learned it in my chemistry class or my physics class, that light is really, color is about perceiving parts of the electromagnetic spectrum. So if you can imagine this, the same things that you perceive as color in the visible are also radio waves and microwaves and also X-rays and all the other things. So it just depends on both the energy of the light that you're putting in as well as its wavelength. So for radio waves can be enormous. They can be the size of buildings. The most common one that people study actually for looking at like distant galaxies is at 21 centimeters. It's a hydrogen line. So it's a line that comes from hydrogen. So they build gigantic radio telescopes out in the middle of the desert and all over the world to see that large wave. But ultraviolet and X-ray is much smaller. Those are sort of on the scale of molecules and even atoms, or even atomic nuclei as we get to gamma rays. And so our perception of color is really limited to a very small window that's right between, around 300 nanometers, that's 10 to the minus 9 meters, and about 700 nanometers. And so in that tiny window, that's kind of where our visual perception is, right about where, and you can imagine that, oops, I'm losing some of my bottom here, but you can imagine that this is just your rainbow colors, red, orange, yellow, blue, indigo, violet, sort of Vib G Roy or whatever, or Yor, Vib G Yor, if you look at it in this direction. And indigo is sort of just a made-up color because Newton was like, he thought it had to be like an even number or something, or 7. He thought it was like the music of the spheres or whatever. But in any case, the main point is that these are just these are the colors that you perceive, and there's a good reason why those are the colors you perceive. Those happen to be where the sun produces the most light. So you could imagine if you lived in, I don't know, off the star of Ceres or something like that, where it's emitting more, where the temperature is a little lower, the color will be a little bit less yellow and be emitting more in the red, and perhaps we would have evolved to actually perceive a different set of colors, maybe slightly more to the red. So that's actually where the majority of the sunlight comes from, is in the UV invisible region, and so that's why we've evolved to do that. Now, if you were an octopus and living at the bottom of the ocean, you actually might be more sensitive to red light or different colors of light. And in fact, there are ways in which that happens. But we're still in this fairly limited range in that window right there. So I'll just take a little aside. This is not my area of research, but it's something I'm fascinated by, which is the area of color perception. So just to remind you, how is color actually perceived? Well, light comes in to the back. It's focused by your lens and other parts here. It gets projected to the back of your retina, and on the back of your retina, you have a bunch of cells, where inside of those cells, there's a bunch of sort of like different membrane layers, and inside of each of those membrane layers is where all of the transmembrane proteins that detect light are. Okay. So essentially, you form an image on the back of your thing, then the light gets detected right over here in the back of this thing, and that forms the neuronal impulses that ultimately you perceive as light, imaging. So we have rods and cones. We have different light receptors, right? You have your low light receptors, which are called your rods. Those are the ones, that's the black curve here. And then you have the cones, which are your highlight receptors. Those are the ones that are associated with color vision. So in fact, when it's dark, your cones are not activated. So you sort of see this thing in this kind of greenish, or like people kind of view it as sort of night vision, grayish thing. That's only your rods that are being activated. That's also your peripheral vision is mostly your rods. So the color vision is the way you perceive color is by differential activation of these different rods. So these are where the blue rods absorb around 400 nanometers. The green rods absorb around 520. And the red rods absorb sort of out into the 600 to 700 nanometer range, which is why I say you can't really perceive light above 700 nanometers because nothing is really absorbing out there. It's not entirely true, depending on your sensitivity, your age, the older you get, the worse you are at doing this. But some people can see light, out to 800 or so. I can't, so, and I'm only, in my mid-30s, so maybe that's a problem. But
what color is it? Is it still red?
It's red, yeah, it's still red. It's activating the red light parts of your eye. And in fact, it might even just be kind of the rods sort of extending their sensitivity because you have so many more rods than cones that those are really, really, really super sensitive. Okay, so how do you actually perceive color? Okay, so how do you actually perceive color? This is just a fun little factoid. You have differential activation of these different rods and cones. So like, if it's mostly mostly blue, you're only activating the blue ones, and so you say that's blue. If you're activating the green ones, it's mostly the green guys, but also some red. And then every color in between is going to be, like yellow, will be activating basically an equal number of green and red cones. And so for that reason, if I want to reproduce any color, I only need 3 types of pixels, right? So I only need a red, green, and blue, color perception, which is why your TVs only have 3 different pixels. They have red, green, blue. And how good they are at reproducing color just depends on how good they are at exciting individual ones of these cones. Now, like about 10% or 8% of the male population, I am colorblind and I'm specifically red-green colorblind. And that makes sense because you see these two are really close together. That's really annoying. So if you have small mutations in your cone cells, it can make these green ones kind of overlap more. And if they overlap more, it's harder for us colorblind people to perceive the differences between those colors. Now, I have the funny story that my mom is colorblind, and if you're a biology teacher, you know colorblindness is an X-linked trait, which means that all of her male children were doomed. So it's a good example of like X-linked traits, so I always use that. So very rare in women, but very, very common in men. Now, obviously, you could also have dichromancy. So that type of colorblindness is called anomalous trichromancy. It means that you're bad at perceiving different colors. You could also have dichromancy where you're missing one of these guys. Some people might be, there's theories out there that people might be super color people, that they have extra cones. I don't know if those have been proven scientifically, but it's kind of a cool thing that you could imagine. So my research, though, focuses on what can we do just beyond the visible, like just beyond where your eyes can perceive. And so if we kind of look, our color stops around 700, and then we have these other windows. We call them the near infrared. We sometimes call sometimes the region above 1,000 nanometers the shortwave infrared. That terminology comes from the military because they like working in this window. That's where they can do a lot of like special types of imaging. And they like using the other acronyms MWIR and WIR for midwave, so 3 to 5 microns, and long wave, like 7 to 10 microns. I think they just like acronyms. It's kind of a famous thing. So most of things that we perceive in our day-to-day lives, the electronic transition, the transitions between electronic energy levels, are in this window here, in the visible, okay? So like this color, the color of this guy or that thing being blue or whatever, most dyes and pigments are in the visible. Almost all dyes and pigments are in the visible or the UV. So every organic molecule, every sort of thread, that's an excitation between electronic energy levels. If we go into the midwave and longwave infrared, we have our vibrations. Like that's where all of the vibrations are happening. That's where if I heat up, that's where like my body heat is producing light at that like 10 micron window. The Earth is producing energy at the 10 micron window. So if you have heat vision, you want to be out in this window. So in here, in this middle region here, it's kind of a spectroscopically quiet region. And we say that in the terms of the perspective of chemical physics, meaning this is a good place for me to do stuff if I don't want other things to interfere with what I'm doing. So there's some really good applications of this type of technology. So the first thing is optical communication. So if we're live streaming stuff, right, through our internet, if you're using Zoom for school or whatever you're doing, it's likely being carried at either 1300 or 1500 nanometers. That's because all of the fiber optics that they string, all the like light-based fiber optics that they string, is almost always being conducted at those two wavelength ranges. They're called the O and C band. Why do they do that? Well, it's because there's very few things that absorb in that window. So it's a good way to send signals over miles without them actually getting depleted. So, for example, at 1550, I can probably send a signal, I don't know, 10 miles effectively, with only losing about 10% of the intensity. And so this was how we do all of our through space communications, or through fiber communications. This is so one of the challenges that we have to deal with is that silicon, which is the primary material we use for your cameras, for detection of anything, and also the primary material we use for electronics. Your iPhone has a little silicon patch on it. If you stare at it, it only absorbs to about 1,000 nanometers, and so beyond that, you can't use silicon anymore. So you need different technologies for that to actually image that technology. So you use different kinds of semiconductors for that, for example. The other thing the reason that these two bands are picked is because water, despite the fact that they said it's spectrally quiet, or there's very few things, water does have a small absorption band in that window. It's where water absorbs just a little bit, but it's enough because there's enough water vapor in the air and water everywhere that it causes some amount of losses. So you want to avoid that water band. And that's really a combination vibrational band. So it's not an electronic band, it's just like these things, the water sort of jostling around, and it has some sort of window right here. The other really cool thing is that if you look, that scatter depends on the wavelength of light that you put in. So so why is the sky blue? Well, the sky is blue because blue light is scattered more than red light, so red light comes down to you, blue light is scattered more. Blue light is higher in energy, so as you go from blue to red, you have less and less scatter. And so you in fact perceive this in this way, and so it lets you can actually image in this window with significantly less scatter. So here's a little experiment we did in our lab, just a sort of proof of concept. Here's a silicon camera. This is a webcam that you can buy them for $10. Here is a IR camera, which we did not buy, we borrowed, but it was about $15,000. Extremely expensive. This is the cheapest one you can buy. And you can do interesting things. So I just told you that water actually doesn't absorb. Water does absorb in this window because of the vibrations. I'm dropping water, regular water, into D2O. That's deuterated water. So water with hydrogens that are twice the mass of they normally are. Because of that, the vibrations have changed. And because the vibrations have changed, it's actually clear in this infrared window, whereas water has some absorption, is opaque. You can actually see something cool that I would not have predicted off the top of my head, but that D2O doesn't really mix with water as well as you would think. They have actually different densities. That's for a lot of very complicated reasons. I actually don't know what the dominant factor is. I think it has to do with the way the hydrogen bonding and D2O is. So you can see stuff in the IR that you wouldn't be able to see normally. So one of the really cool applications are like idea of making invisible dyes. So if I make a dye that does not absorb in the visible, but it absorbs in the IR and emits in the IR, I can't see it under normal cameras. So you can imagine this is useful, but I can see it under special cameras. So you can imagine people using this for things like counterfeit detection, or there's a lot of interest in the military for you want to know that the bomb that was used here was your bomb. This is really dismal but depressing, but it is an important thing. So you'll put a bunch of tracers in that are specific to your type of material. So you want to have something that you can put in that is not immediately perceptible to people, but something that you can trace later down the line. Counterfeit currency, all sorts of other applications like that. The other thing that's really cool, it's hard to see in this guy, but you can see actually through things because it doesn't scatter as much, and there's few things that naturally absorb in this window. So this is imaging through a leaf. You can see the UCLA sign right here. It's hard to see. This is imaging through a silicon wafer. You can actually see the UCLA. I have a better version of this, but I'm sorry. This is imaging through to see the Bay Bridge. I always say it's Golden Gate, but it's not if you're from the Bay Area. You would immediately yell at me, presumably. I don't know. But you could actually, this is a foggy day, divisible camera, and then that same day, the same, just a camera taking the IR, all of a sudden you can actually see in this window. So this is useful. You can imagine applications if you could make cameras that perceive in this window, applications in things like self-driving cars, like that can drive at night or drive, well, not at night, but drive in in high fog, high scattering conditions, right? Which you can imagine is probably pretty important if you're in the Bay Area or in Los Angeles this morning. I don't know if you guys saw how dead so crazy the fog was.
Wait, can I ask you a question?
Yeah, please.
So in the foggy one, we're getting that scattering. The one that you're cutting through, the light that that's seeing was not scattered?
Yeah, so the light is, so the scatter falls off, actually polynomial, or 1 over lambda to the fourth, if you want, for Rayleigh scatter, falls off pretty quickly in this infrared window. And so, yeah, you just get less scatter. So so the main way that this is being used is rather than using cameras, because cameras are expensive. You don't want to have a camera that's $10,000 adding on to the price of your car. They're using these things called LiDAR, which is just a laser radar. And so this is the one thing when I say I'm working on this that a bunch of people ask me for hot stock tips on LiDAR companies because it's like a fairly big investment thing. It's like the new crypto or something. I couldn't tell you anything about which LiDAR company to invest in, but I can tell you that this is a really good way to do range finding in high scattering environments. Needless to say, the other application that I view as the killer application here is basically through skin or through skull imaging. So this is a live mouse. This mouse they've shaved the head, but they haven't put a little window in or anything like that. And this is imaging at 850 to 900 nanometers. Then if you go in specific windows in the infrared, you can see all of the vasculature that underlies that mouse brain, right? And you're doing this through the skin, through the skull, into the mouse brain, because you're in this window where there is very few other perceptible sources of scatter. So this is because the tissue transmission in these windows is actually really, really high. You don't have as much absorption by other random things, and you have a lot less scatter. Those are the two main reasons. So there are a couple of reasons why I find this. Do you have a question? So yeah, the great question. We're using a laser and infrared to excite, or we could use a lamp, it doesn't matter. But this is fluorescence. This is light coming out of the material, out of these guys, and that we're imaging on our camera. So that's how we have the less background. So that's actually a really important problem because we have to find things that not only absorb, but also emit in this window. That's actually the really hard problem. Yes? Oh yeah, so in this case, something is injected. So they have to inject something in. That's another really critical challenge is you have to have something that goes happily into biological material. So we'll talk about that in 1 second. The one thing I want to point out to you all is that I don't know if you know about how these biology experiments are done. The typical version of doing an experiment like this, where they might want to look at this, is they'll put a little window. They'll drill a hole in the skull of the mouse and put a window in it. And this is, imagine, the mouse doesn't like this very much. It's very perturbative. It's actually a hard project. Like, you have to be kind of a gifted surgeon, in a sense. So graduate students spend their entire career being really good at doing this kind of thing. And then they'll measure things like to say, oh, we didn't perturb the mice too much because they're not twitching their whiskers that much. To my mind, as an animal lover, this is a much more humane, at least that's my dream, is that it's a much more humane way to do these kinds of experiments, which could be very important for understanding like tumors and all sorts of other things. So you could do this. This is live imaging of a living mouse. You can see its heart beating. You can see other things. The nice thing is you can use traditional cameras, so you could just do what is like video rate versions of this. Now, the expensive cameras, but you can still do video rate, and you can actually do things as this thing moves around. This is a zoom in of the heart. It's cool imaging. So how do we do this cheaply? Well, I just told you that cameras are really expensive in this window, right? So your iPhone camera, does anyone know what an iPhone camera costs? Any guess? So 50 or 1,000. So you have 3 right now, or some of the new iPhones. They're about $10 each or so. Now they charge you about $1,000, but but they are incredibly cheap. They've nailed this down, and those cameras used to be like back when I started working in a lab in like 2004. The equivalent cameras, those were like $10,000. Now they're like really dirt cheap. A crappy camera is $10,000 to $15,000. A good camera in the near infrared on this window is about $100,000. So it's still not so this is like an ongoing research question. Like, how do I drive this price down. So this is a little bit about my research, a little bit getting into my actual research questions. So we want to find things that absorb and emit in this spectral window. Like I said, there's not many things, but there are a few. So for example, there are dyes, organic chromophores, and the ones that we study tend to be these types of dyes. They're called cyanine dyes. Doesn't really matter the details. They just happen to be very good for this type of imaging. There are, the ones that were actually done for this were carbon nanotubes. I don't know if you guys learned about these, but these are like long carbon nanotubes. But from the perspective, they're really cool and they work really well. But from the perspective of like getting this into like a human imaging study, it's basically like injecting asbestos into you. So we would never be able to do that. These actually have a chance to be technically clinically approved, right? Because actually there are versions of these dyes that are already approved for imaging. Some of you guys may have even had this if you've had like certain angio, I forget what the thing is called, but like certain types of treatments, they'll inject this dye as a tracing agent. What?
Oh, I had it.
Oh, exactly. So you know so this is common. It's not necessarily like the healthiest thing in the world for you, but it's also still like relatively non-toxic. No, these are actually the nanotubes themselves that they're using to image. That's a good question. But because there's very few things that absorb and emit there, but nanotubes are one of those things. Yeah. So one of the things I'm going to tell you about today is semiconductor quantum dots. So I was just telling you that silicon does not absorb in this window, but there are semiconductors that do. And so the kind of ones that we look at are, the ones that actually work in this window are mercury, sulfide, selenide, telluride, lead, sulfide, selenide, telluride, indium arsenide, a handful of different ones that actually do absorb and emit in this window. I'm not going to pretend like we're going to use this for human imaging because, again, we're not going to inject mercury into people. They're super heavy metals, but we work with these in our lab, and we try to be very safe with them. Obviously, I'm not going to lab wearing flip-flops and, you know. So these are, now what makes these special is not that they intrinsically absorb and emit in this window, but what I can do is I can take them, make them really small, aka quantum confine them, or make them tiny, make them nanomaterials, and by doing that I can tune them so that they go from absorbing and emitting like way in the infrared into to absorbing and emitting in this window. And so that's what we do, that's our trick, is we kind of make these really small and so that they absorb and emit in this window. So let me just remind you all, and also sometimes remind myself, what a semiconductor actually is. So semiconductors are materials where they're literally elemental materials or binary materials, salts. They're actually literally salts, so you could be like cadmium telluride or whatever. That because of the way that they combine, they form a band gap. Those band gaps are like separations between their energy levels. They're filled orbitals with the filled electrons and unfilled orbitals. And they can be pure elements. So things that actually, in a pretty predictive way, like, again, the periodic table is always the chemist, like it's the secret to being it's like superpower, basically. Like I can just look at the periodic table and be like, oh yeah, this is going to work and whatever. But like silicon, germanium, carbon, are in their pure material form are semiconductors. Carbon's pure material form you may know as diamond. Diamond's a weird kind of semiconductor. It's a really big band gap, but it is technically a semiconductor or an insulator. It is, once the band gap's big enough, you say it's an insulator, but that's the big idea. And then you could actually play games like, literally like, okay, cadmium sulfide, so this is group 2,6. Don't ask me why that's the old naming convention. It's like group 2B or whatever is this guy here. So cadmium sulfide, selenide telluride, mercury sulfide, selenide telluride. Those are 2,6. You could do 4,6, which are lead selenides. Don't ask me why, but they do actually work, and you can kind of predict, oh yeah, tin sulfide, that'll be a semiconductor, so that does actually work, surprisingly. There are exceptions, but you get the idea. So if I take a semiconductor and I quantum confine it, what I can do, if I make it really small, is I can effectively make it like what we call like a particle in a box. So like when this thing gets really small, the electron no longer can go over the whole semiconductor. The electron has to stay in this small confined region. And because of that, it opens up the band gap. It moves those band gaps so they're farther and farther apart from each other. The bigger the band gap, the bluer the wavelength of that it can absorb and re-emit light, right? So blue means higher energy, bigger band gap, et cetera, et cetera.
You mind just do that again a little?
Yeah, of course. So think of it this way. If I have a big particle, the electron can go over the whole thing, and I just feel the bulk material band gap. As I bring that system together, then all of a sudden, the energy levels between the ground state and excited state, or the band gap, get bigger and bigger. They get bigger. As they get bigger and bigger, it makes the energy levels farther apart. The farther apart they are, the higher the energy is that they absorb and emit. The higher the energy absorb and emit, the bluer the wavelength of the system. So some of these materials, like the ones I was mentioning, mercury telluride, for example, they don't even have a band gap. They're like almost a metal. They don't have a band gap when they're in the full thing. But as I make them smaller and smaller, I can tune that band gap all the way from the long wave to the mid wave to the short wave infrared. And so that's actually the trick we use.
One thing I was trying to use, I feel like this might be the point where you need to differentiate. This is different from what we were talking about earlier because the atoms and the elements we were using were just gold and metal. So you didn't have any band gap. That was just conducting because the electrons were able to delocalize between them.
Exactly, yeah, that's right. So these are salts or whatever, so they're not intrinsically conductive. They have this band gap. And then like gold, which has half-filled orbitals so that it has any number of states that it can go into. But, so you have there are the confinements in the plasmon. Anyways, it is related but different, you know. So once again, in my group, we've been really interested in these mercury chalcogenide materials for all of the reasons that I just discussed. And we actually take these guys from having, well, they actually say negative band gap. It's a weird terminology, but it means it's a metal. And they can quantum confine them all the way through the visible. And we can make other materials. So we do this through chemistry, through wet solution phase chemistry. So I mentioned before that, you know, there's different ways to make nanomaterials. Well, I didn't mention it, but I'm sure you guys have talked about it. But the way that we're doing it is literally probably very similar to the lab you just did. We take salts, we stick them into a thing. In this case, this is a high temperature synthesis, so you have to heat it up in a long chain alkane. So like you take it in octyl decylamine, so it's like this really long chain alkene, or octyl decyl, whatever it is. Yeah. Sorry, I don't do the chemistry. My students do it, so I don't have to worry about it. So we heat it up to a very high temperature, and it takes the salts and it forms these tiny nanocrystals, which we can control the size using temperature control, using the precursors, using all sorts of other chemical tricks. And then this reaction, depending on how long we wait or our particular sets of controls, we can make like very small materials that are all roughly the same size. This is a great, actually kind of a cool example of like actual basic chemistry leading to real applications. So my postdoc advisor developed this method in like 1990 and refined it, and now you can walk into every Costco and buy a quantum dot television where they now can make every single quantum dot is exactly the same size to within one atom based on the wet chemical method, which is extraordinary. I mean, that's precise control that you wouldn't be able to do like with an electron beam lithography method or anything like that. So it took, 25 years for that to happen. But in the intervening 25 years, we saw something really amazing happen. It become a very commercial technology. In my group, we do something a little bit different. We actually study these things called nanoplatelets. So nanoplatelets are, instead of being a quantum dot or a spherical particle, it's a 2D sheet. And these 2D sheets have only like 4 atoms. They're only like 4 to 6 atoms thick. But they're really, really large. And so that gives me the quantum confinement along one dimension, but along the other dimension, I can like absorb all of the light that comes into the system. And so it's a fun playground for looking at different properties, extreme confinement. So instead of having confinement in all 3 dimensions, I now have really 4 atoms thick. And we can actually make these guys just by controlling the temperature and some of the conditions of the reaction. So actually, you have that type of control. In addition to making spherical nanoparticles, you can make rods and sheets and all sorts of other stuff. which was, some of it was incidentally discovered, some of it was by design, but that's kind of the idea. We can actually make, in our case, we're making cadmium telluride nanoplatelets, which we then can add in mercury salts, and those will actually replace the mercury. Cadmium 2+ will be replaced by the mercury 2+ because of salt reasons. I don't remember. No, I mean, there's like theories of hard salt, soft salts. I couldn't actually explain them to you, but maybe you guys know them. And then one of the things we do is we can then tune this further so that it absorbs and emits in the infrared by actually creating traps in the system. So what we'll do is we will kind of roughly treat these nanoplatelets, and then they form little like clusters on their surface, and those things actually can then emit light. So that's something we've been doing to make tunable nanomaterials. How much time do I have? Am I good?
Maybe like a couple more minutes?
Okay, great. So I'll just wrap up. Let's see.
What's the application?
Right, good question. So there are a bunch of different things we're interested in doing with these types of materials. So this is a good slide for that. So one area that we're really interested in is the ability, since I can tune the size, I can do different colors. And so let's say I want to tag a bunch of different things in a living system, like, the inside of the cell, the outside of the cell, the mitochondria, the whatever. So I can now, instead of just doing that in the visible, I can do that all through the infrared and then image that deep into tissue. Another advantage is the ability to do this in a cheap and scalable way. So I can make molar, that's the magic trick of chemists, is we can make molar quantities of identical things. The mole is 10 to the 22 versions of that. That's amazing. You can't make 10 to the 22 computer chips, but you can make 10 to the 22 of atoms very easily. So we could do this, and we want to do this scalable. So this is a synthesis that we used to do, where you actually make such a large amount at a time that the way you can do this is by injecting really fast. So you have to use like an air gun to shoot the precursors right in, so all the reactions start at exactly the same time. This is called fast injection. But it's probably the only synthesis you use a gun for, which is a joke that kills in other places. But you can then use these guys to make solution processable electronics. So then I can use these guys not just as emitters, but then to drop cast them onto a surface, just like they make a silicon iPhone, but now I'm drop casting this guy, and it's taking the light and producing electrons that I can use for other things. There's some other cool applications where you could take these, have them absorb infrared light twice, and then convert that into one visible photon. So I could use that to detect stuff in my camera or in a normal cheap camera. That's called upconversion. That's a really cool process. And then, so like one of the things that I just find really exciting is maybe we could take these really cheap materials, drop cast them on a surface, either doing these upconversion or just directly detecting it, and we can actually detect infrared on a very cheap platform. So I can actually detect this light just, instead of buying a $100,000 camera, I can make something really cheap. And then it could be omnipresent, and the application space may be way beyond what we can see. So for example, could we see, people have noticed that bad apples will have infrared splotches on them. That would be something you could see. They've looked at this for quick detection of cirrhosis. Like you can see this some things in cirrhotic livers, all sorts of other things. So this is just ideas out there, but yeah. Thank you.